To find the pH of 0.1 molar of sodium hydroxide, first we need the dissociation reaction of the sodium hydroxide in water. Since sodium hydroxide is a strong base, it will fully dissociate into Na plus ion and OH minus ion. Then, construct a reaction table that contains the initial concentration, change in concentration, and final concentration. Initially, there is 0.1 molar of sodium hydroxide and 0 molar of the ions product. Since sodium hydroxide will fully dissociate, sodium hydroxide will decrease in 0.1 molar and the sodium ion and hydroxide ion will increase in 0.1 molar. The final concentration of the sodium hydroxide is 0 molar, while sodium ion and hydroxide ion is 0.1 molar. Again, remember, for the change of concentration, it still depends on the stoichiometric coefficient of the balance equation. If there is 2 moles of hydroxide ion, the value of the change in concentration must times with 2. Since we only have the concentration of the hydroxide ion, calculate the value of the POH first because POH is equals to negative log concentration of OH minus. We will get the value of POH which is 1. Since pKw is equals to pH plus POH, the value of pKw is 14. Thus, the pH of the solution is equals to 14 minus with the value of the POH. So, in this reaction, the pH of this solution is 13. To find the pH of a weak-base solution, same like strong base just now, we need the dissociation of the base in water. So since ammonia is a weak base, so it will dissociate very slightly into ammonium ion and hydroxide ion. Since we have an OH minus ion in the equation, we need to find the value of POH in order to find the pH of the solution. To do that, we need the value of X. So, use the base dissociation constant to find the value of X. The Kb expression for this reaction is concentration of ammonium ion times concentration of hydroxide ions divided by concentration of ammonia. Substitute the value of concentration of each species at equilibrium into the expression. Since Kb is very small, we are going to assume that 0.1 minus x approach to 0.1. Thus, x is equals to 1.34 times 10 to the power of minus 3 molar. Check our assumption by using the percentage dissociation of the base, which is x divided by the initial concentration of the base times 100%. The percentage dissociation is less than 5%, thus our assumption is justified. Since x is equals to concentration of OH minus, the POH is equals to 2.87. To find the pH of the solution, pH is equals to pKw, which is 14, minus the POH, we will get 11.13. The higher the concentration of the hydroxide ion, the larger the value of Kb, thus the stronger the base. Since pKb is equals to negative log Kb, the larger the value of Kb, the lower the value of pKb, thus the stronger the base.